the example that I did in the class on week 7 on the 17th of November. There was some minor errors in the Excel, so I just want to correct those, make it a bit clearer. So we have this question. Remember what the class was? It was looking at a question that I hadn't seen before, how you'd set up a new Excel sheet, really based on what you'd seen in other Excel sheets, but doing one right from scratch. So we've got a question here, which is a trapezoidal channel with a bottom width of 4 meters, a side slope of 2.5 meters, and has a flow of 30 meters cubed per second. The channel falls 1 meter in 1.5 meters, and a Manning's N of 0.5. Right, if and the question says, if the channel has an outflow where the water level is 10% above critical depth at the downstream end, determine the flow depth at 80 meters upstream. So this is 80 meters now, which makes it a much more sensible iteration. Calculate the solution to 2 steps of integration, which you could do by hand, 10 steps and 50 steps to see what we get in the changeover accuracy. So first thing to do is write down all the things that we know. So I'm going to write down G, which is 9.81, because we're going to use that. Let's put put the right units in, meters per second squared. Get that so it looks right. You don't actually have to do that, but and I usually colour general information that we've been given in this yellow, so that the bed slope S0, well, that's 1 in, and we're told 1.5 kilometers, so 1 in 5,000. Probably colour those two in yellow, as they're given, and we calculate this S0 is equal to that one divided by that 1500. Let me just oops, not insert, show that that's a couple more decimals, so I'm showing 3 significant figures on that one. The flow rate we're told is 30 meters per second, so 30, we'll put 0 meters cubed per second. Tidy up that format as well. Superscript for 3. Okay, meters cubed per second. That's in the yellow version value. We've got Manning's N. We've got the bed width. We've got S, side slope, and we've got the distance up to upstream, which I'm calling X. Let's just put those values in. So 0.015 from N, bed width was 4 meters, not meters cubed. Side slope 2.5. And the distance upstream, we've got this 80 meters. Right, those are all given values. I'm going to colour them in yellow for reference. Question also says, do it in 2 steps, 10 steps, and 50. So do n steps. 2, 10, and 50. Okay, right. Now we're going to enter in various equations in our iteration. So let's just get a good reference to those, and I usually try and put these on the screen. So I'm going to copy from another spreadsheet or from the notes these set of equations for the various geometric parameters of the trapezoidal channel. I'm going to just write down the equation, the general equation for backwater curve, the gradually varied flow, which when we write in a differential form, we're calculating, we want to calculate the dy in this term with a known dx. The dx is 80, total x is 80, so that's known, so that's the one that's known. Okay. The SF and FR squared terms, let's just write those down because we're going to have to type those in. So SF, don't recall where that comes from, then go and check. And FR for a general, FR squared, sorry, for a general equation, shape channel, any shape channel. Now, we need to work out what iteration method we use. So the direct step method requires an average value of y, and we don't have the value of y further downstream because that is what we're about to calculate. We don't have we don't have that y, so we're going to have to use something that uses the initial data. So what we can use is an Euler method, and the Euler method simply uses the initial value. So we're going to essentially approximate that large term in brackets by the values at the initial known point, or sometimes I'll write this down. The equation we're going to write and solve in our table as this. And I'll write this down. This is a Euler method. What would be would be more accurate, second order, is the Euler improved method. We could apply the Euler improved method here, and that would be ideal. However, it's a little bit more fiddly, so we're not going to do that, and I wouldn't expect you to do that in an exam. But what we'll investigate is how many steps does increase the number of steps increase the accuracy, and does it converge to towards a constant value. So let's start setting up an iteration. So let's just do the 2-step one. So n steps. I'm going to write as 2 here. Y naught. Okay, so I haven't discussed y naught. So what's the starting value of y we're going to use? Well, the question says it's causes the water level to be 10% above critical at the downstream end. So that's our y naught. So actually what I need to put in here is a downstream depth factor. Just adjust that slightly so it's there, of 10%. Okay, so then we can work out our Y naught, which I can tidy up, to be equal to the critical depth. So we need to calculate critical depth. But before we do anything else, I'm going to get rid of those. Let's calculate critical depth. So normal depth and then critical depth. So normal depth, how do we calculate that? Well, we go to our spreadsheet that we've seen before, and I'm just going to show that spreadsheet. Oh, here's my spreadsheet, which I'm going to enter in my values of Q of 30, N of 0.015, B of 4, side slope of 2.5, and bed slope of that. And this iterates either by a trial and error method, or we can change the trial and error method to so it should be higher, 1.8. Let's look at 1.85 is good there, and actually the secant method just did that straight away, so no need to do the trial method. So the normal depth here, 1.847. 1.847, that's meters. I'm going to colour that one in sort of pinky colour, so it identifies it as a calculated one. We need to then calculate the critical depth, because we're actually going to use that one here. You zoom into that so it's a bit clearer. So we're going to critical depth. We've got B as 4, side slope is 2.5, Q as 30, and we'll see if we enter some trial and error values, you get to about 1.35 there. So that's down to 1 litre a second accuracy, and 1.329,347. And so here we are. Okay, 1.35 actually is as accurate as we're going to get there for 3 decimal places. So 1.350. Again, meters, and I'll highlight that as that same color. So normal depth here is above critical. So we have subcritical flow. It's a mild channel. So what we're going to get, if we're starting just above critical, we're going to get an M1 profile on the channel, rising up from the downstream end. Okay, so now we need to just find our Y naught value, our starting value of the iteration, which is based on 10% above the critical depth. What I'm doing here is formatting that to be a subscript. So Y naught will be equal to the critical depth times 1 plus, well, it's our 10%, so 10 divided by 100, and that should be a little bit above critical depth. So are they meters? I'll use the same indicator that we've just calculated that. Okay, so we're going to iterate between from 1.485 80 meters upstream to find out what the depth is. We're not going to use this normal depth at all. We've only used it in identifying that this is a mild channel and the depth is going to increase because we know it must be increasing towards that. Okay, that's the only reason for calculating normal depth. So let's start with our iteration. So first one will be just 2 steps. Number of steps 2. Our y0 value, well, this is our y0 value. I'm going to put it in this block here because it'll be useful later when I cut and paste the table. Our x is going to be equal to the minus, it's going to be minus this 80. Okay, because we're going backwards up the channel. Remember that to get the sign right here. And we need to calculate the dx. Get that format cell. Maybe get the symbol font, and it will show a nice delta in there. Okay, delta x is equal to the x divided by the number of steps we're taking. So it's 40 meters. Okay, it's easy. Right, so let's just set up a table now. It's up the way, and the table will have enough to calculate these parameters. This is the equation we're going to solve, the Euler method we're going to use. Second. Okay, so let's have a count in the first column. I'll count at 0. That just tells us the iterations. X, distance along the channel. Y, the depth, cumulative depth. Well, we're going to calculate the surface width. Let's put some units on here. Let's just do it properly. Y, B in meters. Capital B, remember that's the surface width. A in meters squared. P, metric perimeter in meters. R, in this also in meters. SF and FR squared, and then the dy. Okay, that we're going to calculate. We could tidy these up if we wanted. Get them looking a bit neater. Rather than go looking for that font, I can just change this to right, dy. This is in the table. Let's just put a grid on it so it's a bit clearer, clearly an iteration. So x, well, we're starting at x, so we're starting at 0. So I'm going to type in 0 there. Y, well, y0 is equal to this y0 value that we've just calculated, 10% above critical. I'm going to use 3 decimal places for this y. The width, top width, well, it's b plus 2sy if we're looking at the formula table here. So let's type in that. So the width, let me just reduce the screen size slightly and we'll get everything on here. Okay, so equal to b, so the bed width, which we need to F4, get our dollars a fixed value, plus 2 times the side slope, F4 of that, times our current value of y. Okay, we need to work out P, sorry, A, work out A, which is equal to, we need to bracket the bed width for fixed with Fy plus side slope times y, close bracket, and times all that by y. Yep, P, there's our P value. It's a bit longer equation. Let's type that in. B, bed width fixed with F4 plus 2 times y times the square root of 1 plus the side slope for that all squared. Okay, R, easy one, this is just A divided by P. SF, well, here's our SF equation. Let's bring that a bit closer so we just remember what it is. SF is equal to the Manning's N fixed squared times the Q fixed squared divided by, I'm going to put some brackets in here just to make this a bit clearer. So all the denominator I'm going to put in brackets. R, so they need brackets here, 4/3, or you type in 1.3333 times the area squared, and I'll close bracket, and I get SF. Right, I've got 3 significant figures. That's actually going to be a bit smaller as we go on. So I'm just going to increase the significant figures slightly to 1 extra. The Froude number squared, let me just remind you what that is. That's the Froude number we're going to put in. So that's equal to the surface width, which is that B, times by the Q, which is up there, and that needs fixing and squaring, divided by the area there cubed, divided by G up there, which I need fixing. Okay, Froude number is probably not too accurate to there, so let's just reduce that to 3 significant figures for our table. And dy is just now applying this formula here. So equals delta x, and the delta x comes from here, which again will need fixing, times by S naught, which is up here, again needs fixing, minus SF, close bracket, divided by 1 minus the Froude number squared. Okay, so we've got a dy here. So I count here is going to be the one before it plus 1. Our dx is going to be equal to the one before it plus delta x, and that needs fixing. The y is equal to the one before it plus that new dy. Okay, so it's gone a bit deeper. Let's just fix these decimal places on that. 3 to the millimeter. Okay, so we can now drag those down. Let's just put the cells on the grid on, and actually we just need to do one more row to get it to minus 80 meters, and we see that the depth there is 1.655 meters, and that's the answer that the question says after 2 steps. Let's do this again for 10 steps and see if that answer changes. So what I can do is highlight all of that lot, copy it and paste it here. Right, I'm going to put 10 in here, 10 in here. Okay, some things have gone wrong, but let's tidy it up. So this should be y0 is equal to the y0 we have before here, and I'm going to put that as a 4. We can do the x is equal to the minus 80 for that, and the delta x is correct. It's 80 divided by 10. Look at that. Minus 80 divided by 10. Looking at this table, actually we just need to correct 2 things on this. This delta y was based on a fixed value of delta x as being 40, but we need the one that's relative to this table. So we need that one. We need to drag that cell down. And this delta, this was also equal to the one with that delta x step. So we need to just correct that one for that cell. Okay. So highlight that second row, drag this down so we've got 10, 9, and drag this one more down so we get the last value, and here is our last solution value. So at minus 80 meters, which is where we want to be, the depth is 1.623. So it's a little bit different to the 2-step ones. How much? Well, it's 3 centimeters over 80 meters. In practice, probably not worth worrying about, but 2 centimeters over 80 meters. Let's do it at 50, as it asks us to do. So we'll highlight, in fact, just highlight down to the just before the last one. Paste that in. Okay, it's looking the same. Good. So we change this to 50. We need to change the delta y calculation so that it's not using that. It's using the right delta x. And we used to change that one so it's using the right delta x. Okay. If we double click on that one, it corrects it all. In fact, probably just drag that. So let's go down to 50. Right, guess there a little bit further. Drag it down. So I've gone too far. Let's delete those last ones, and we can delete those as where we're indicating 50 or minus 80. So we see now 1.618. That's the answer here. 1.618. 161.8 centimeters, but 161.8 meters, 162.3. So what's the difference there? It's half a centimeter. over 80 meters. So it's converging towards that value. And I would say that's accurate enough. Okay. So this is how you could compare three solutions and do a quick copy and paste. Do remember to make sure you get your dx's and dy's right when you're doing your calculation. Okay, those are highlights. Okay, so I'll finish that. Stop the recording.